Hello and welcome to Chapter 1.4 from Stevens' Matrices, Vectors, and 3D Math. In this chapter we're going to talk about vector spaces. And specifically we'll be talking about the vector spaces R2 and R3. Right? And R2 is just 2D and R3 is just 3D. Right? And that fancy R, say for example R2, that just looks like vectors of this form. Say we have a 7 and a -2. Alright, this funny looking R in here means there's a real number in the first position and a real number in the second position. Alright, and then the vector space R3 just looks like ordered triplets, 7, 2, -3. Alright, so there are three real numbers. Okay, so we're going to do a little motivation for this chapter, and actually for the next couple chapters, but I'll switch to full screen mode for that. And we have here an ellipsoid in 3D. So in this case we're going to be talking about R3 in 3D, and we'll have an ellipsoid and a unit sphere. An ellipsoid has the radius vectors that aren't the same. For example, 3 in the x direction, 2 in the y direction, and 4 in the z direction, for example. Whereas a unit sphere, the radius direction in all directions, or the radius vector, sorry, the radius length in all directions is just 1. Right? And so if we're in 3D, if we're in 3 space, we have various characters that we're trying to either model or animate or display on a screen. So suppose we have a character, right? Like this. And we want to find out if this character has run into things or if things have hit this character. Well, it's hard to tell if something has hit the character because the character might have a very complicated shape, right? It's got some legs, some arms, some head, or maybe it's, a race car that's got some weird shapes. So it's hard to tell exactly whether that object has intersected with or ran into something else. So what we'll often do is we'll take this character, like our guy here, and we will enclose the character in an ellipsoid, right? And what's nice about this ellipsoid, sorry, I erased his head. What's nice about the ellipsoid is that it's a little easier to tell if the ellipsoid has run into something. But it's not that easy. It's much easier if we can take that ellipsoid and then turn it into my unit sphere. And I'll do that with some sort of transformation. That changes my enclosing ellipsoid into a unit sphere. And here's the beautiful thing about the unit sphere. If I have a point here and I want to know whether it's in the unit sphere or not, if there's been a hit, if there's some intersection with something, this is really easy to do. I take my point, say it's just xy. I just get this distance right there, d. If that distance is bigger than 1, it's not in the unit sphere. If it's less than 1, it's in the unit sphere, right? So collision detection is much easier when I'm dealing with the unit sphere than if I'm dealing with the ellipsoid, right? And so the transformation that we do to go from the world where I have ellipsoids to my world of unit spheres is actually called a change of basis. A change of basis transformation. All right, so we're going to deal with, we're going to determine what a basis is. What is a basis? How do we know when we have one? And then later, how do we change the basis? Right? And so you can sort of think of this as a motivation. How do we do this transformation so that my ellipsoid becomes a unit sphere? Okay, so let us move on. Okay, so if this was a real course in linear algebra, this would be a much bigger section or chapter. It would be quite a bit of the course. And it's talking about general vector spaces, right? And so we're going to define what a vector space is. But as we're going through these definitions, they're actually properties. As we're going through these properties, just think of the vector space R2, which is just the set of real numbers, say 1, 7, 3, 9, 2, 4, things like that. All right. R2 doesn't equal that, but 1, 7 ordered pairs are what I'm talking about when I talk about R2. If this was a more of a general linear algebra course, there's all sorts of vector spaces, vector spaces of polynomials of various degrees, but here we're just going to be looking at R2, R3, and Rn, Okay, so a vector space is a set. We usually denote it with the capital V, and the elements of that set are called vectors. We will often denote vectors within that set with X or Y or Z, and we would say X is an element of V. A vector space has two operations, addition and scalar multiplication, and they satisfy a bunch of properties. Right, so we'll go over these properties pretty briefly, but if you think of R2 up here, it should be fairly intuitive, right? So the first thing we have is addition. It's a binary operation, and for example, if I have one element X in my vector space and one element Y in my vector space, then the element X plus Y defined by my vector addition is also in that space. And that's certainly believable in R2 because if I have any two vectors, say 1, 2, or any two numbers you want to pin in there, 3, 5, if you add them, you get 4, 7, and that too is an element of R2. Right? So it's closed under addition. It means if you take two vectors in the space and add them, the sum will be in the vector space. Okay, so next property of vector addition. For any vectors x, y, and z, you can group them however you like. You can group the vector addition however you like. You can group the first two or the last two. And addition commutes. X plus y equals y plus x. And again, that should be fairly intuitive. There is a zero vector in my vector space such that x plus 0 always equals x. And the zero vector in R2, if you have any vector, I'll just use 1, 2. If I add 0, 0, I get that vector back. So this here, that's my zero vector, denoted in the book as a bold-faced 0. So we have an additive identity, known as the zero vector. We also have an additive inverse. Right? So if I have any vector in my vector space, there's the negative of that value, or that vector. And so for example, if I have 1, 2, again, 1, 2, then its additive inverse is negative 1, negative 2, which gives me the vector 0, 0. It gives me my zero vector that I was just talking about, right? All right, so our vector space has to have an additive inverse, and we have to have this scalar multiplication so that if I have an x, a vector in my vector space, and alpha, a scalar, which is just another way of saying a real number, then alpha times x is still in my vector space. Right? For example, if I have 3 times 1, 2, that gives me the vector 3, 6. That's still in the vector space. I'll never do this and suddenly leave the vector space. I'll never take a scalar times a vector and wind up with something that isn't also in my vector space. Okay, so scalar multiplication has to satisfy a handful of properties here. You can distribute across vector addition. So basically what you're doing is you're distributing scalar multiplication across vector addition. You can distribute scalar multiplication across just standard addition. Those are just two numbers. All right. There is an associative property with the scalar multiplication. That means you can take alpha times beta times x is the same thing as alpha times beta times x. Just doesn't matter how you group them. And then for every vector in my vector space, there is the scalar multiplication 1 times that vector. That's a crazy looking 1. will always return the same vector. Right. Scalar multiplicative identity is just multiplying by 1 when we're dealing with R2, R3, things like that. So R3, so those are the properties. It seems like a lot, but they all should be fairly intuitive when you think about R2, like ordered pairs. When you add them together, you get an ordered pair. If you multiply one by a number, you get an ordered pair, and things like that. Right? Vector space R3, to formally define it, looks like this. It's the set of all vectors with 3 terms, where x1, x2, and x3 are just real numbers. And there's an example. All right. R2, and we just sort of did this at the very top here, is the set of vectors with 2 terms, where x1 and x2 are elements of the real numbers. And there's an example of a vector in R2. The vector space Rn looks just like R2 and R3, except it has n terms. All right. And so what we're going to do, in order to get to this basis and what a basis is, we have to talk about this thing called linear combinations. Right? Linear combinations. And basically, what we're looking to do is to combine vectors through addition and scalar multiplication. So suppose I have my vectors, v1, v2. So those are vectors in a vector space V. And I have a1, a2 to an, and those are scalars from the same vector space. Think of them as real numbers. Then any vector x that looks like this, the first scalar times the first vector, plus the second scalar times the second vector, plus on and on and on, last scalar times the last vector. Any x in that form is called a linear combination of those vectors. The scalars, the a's, are called the coefficients of that linear combination. Right? And so now I'm going to show you how to generate linear combinations, because it looks like sort of a nuisance to write all this out, and it is. There's actually a fast way to create linear combinations. Right? And the way we do that, if you take this linear combination that we wrote up here, I'm going to rewrite it right there. All right, so there it is. That is more efficiently written as matrix multiplication, where this m just has the first vector as the first column, the second vector as the second column, on and on and on. The last vector is the last column. And this column vector A are just the coefficients in the linear combination. Right? So you can generate linear combinations very easily through matrix multiplication. So here's an example. Suppose I have v1, which is -1, 0. And I'll put it in column form. v1 is -1, 0. And v2 is 3, 4. Right, find the linear combination -2 times v1 plus 5v2. And this is easy enough to do by hand, but let's do it through matrix multiplication. So there's v1, first column, v2, second column. There's my first coefficient, -2. There's my second coefficient, 5. And if I perform this matrix multiplication, I have -1 times -2, 2, plus 3 times 5, 15, so I get 17. And then if I take, going for the second term, 0 times -2 plus 4 times 5 is 20. All right? And that doesn't look like the same linear combination up here, but let's just check it to make sure. All right? I'll put v1 and v2 right below this. So that's -2 times v1, which is -1, 0, plus 5v2, which is 3, 4. So that's going to be 2, 0 plus 15, 20. Lo and behold, 17, 20. So when we create linear combinations, we just use this form here, where the matrix has the vectors and the column that you multiply, the column vector you multiply by, are the coefficients. So that's, determining a linear combination. How about if we determine, how about in this next case, we're going to determine what the linear combination needs to be in order to get a variable out here, right? In this case, in this first problem, I said, all right, here's V1, here's V2, here are the coefficients. What's the result? X. Now I'm saying, suppose you have X, what are the coefficients needed to get that vector, right? So for example, consider the vectors V1, V2, and V3. Express this vector X, and I'll write it over here in column form. 4, -1, 14. Express this vector as a linear combination of these vectors, right? So that means we need to find the coefficients A1, A2, and A3 so that A1 times V1 plus A2 times V2 plus A3 times V3 gives me my vector X. Right, so I have three unknowns, right? But that's actually quite easy to do if you put it in matrix form, right? There's V1, there's V2, there's V3. Here are my coefficients, A1, A2, and A3. Those are the values I don't know. And here's that value of X that I'm trying to hit, right? And so this is great. It's in matrix form. This is usually where the unknown is sitting, right? If you think of AX equals B, right? Unfortunately, we named this X, so I can't quite use that. I can't quite use those variables, but it's the same problem. I'm looking to find that column vector. And so we will look at it like this. We have V times A equals X. So A is just going to be V inverse times X. Or in MATLAB, it'll be A equals V backslash times X. But in order to do this, or even write it, I should at least put this, provided V has an inverse. Right? Or V is invertible. V is invertible. And as we saw from the last chapter using our super theorem, that means the determinant of V cannot equal 0. But if the determinant does not equal 0, it's fast, it's easy, you get a unique solution, and you can figure out what those coefficients are. And if you do that, and you could do it by hand, but I did it with software, you get those are your coefficients. So A1 is -2, A2 is 0, A3 is 3. All right. All right, so let's take a look at the standard bases for R2 and R3. They're so standard and they're so easy to use. They're fantastic bases, and you'll see why in a second. But in R2, the standard basis looks like this. E1, that's the first vector. E2, that's the second vector. And the wonderful thing about this basis is that if you have this vector 2, -2, if I want to find out the linear combination of my basis vectors that hit that vector, that return that specific vector, it's just 2 times E1 plus -2 times E2. Right? In other words, the coefficients of the linear combination are sitting right there. It makes the whole thing seem redundant and almost silly, right? And it is redundant, but that's because this basis is so convenient. When we start dealing with other bases, it's not quite so trivial, but it is trivial with the standard basis. And same thing for R3, only the basis vectors get a little bigger. I get E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. And if I was on in R4, R5, that pattern would continue. Right? Okay, and again, the wonderful thing about this basis is that if I want to find the coefficients of a linear combination of these basis vectors that produce some vector, say this vector here, the coefficients are just right inside the vector. So it's 2 times E1 plus -3 times E2 plus 4 times E3. Right? So it's super convenient, super easy. But as we start using other bases, it gets a little trickier, and so just understanding this concept of a basis is important at this point. And so that wraps up chapter 1.4, and I will see you in chapter 1.5. Bye.